All right, so we are looking at indeterminate differences. And what we mean by indeterminate difference is infinity minus infinity. And it's just the difference. We could definitely take the sum of infinity. Infinity plus infinity is just infinity, right? So we're just going to be talking about the difference. And an example of this could be something like this. The limit as x approaches 0 of the cosecant minus the cotangent. And if we were to plug in 0, cosecant of 0 is infinity, and the cotangent of 0 is infinity. Okay, and this is an indeterminate difference. And again, this does not equal 0 because they might not be going to infinity at the same rate. Okay, so it's not guaranteed to be 0. So what are we going to do? What's our strategy? So our strategy in this case is, again, to get back to a quotient like we were doing before. And then once we have a quotient, we can use L'Hopital's rule. All right, so we're going to manipulate back to a quotient. So let's take that limit, except instead of cosecant, I'm going to write that as 1 over sine. And instead of cotangent, I'm going to break that down in terms of sines and cosines. And notice when we do that, we have the same denominator. So we can very naturally get back to a quotient. We can combine or do the operation to the numerator, then keep the denominator. Okay? And then if we wanted to evaluate the limit, maybe remember our first step is always to plug in that 0 to see what case we're in. And if we plug in the 0, 1 minus cosine of 0 is going to go to 1 minus 1 over sine 0. All right, so 1 minus 1 over 0, we're getting that indeterminate form. Okay, so that means since it's indeterminate, we can use, whoops, it's a person, so it should be capital, L'Hopital's rule. All right, so again, what's that rule say? It's saying that this limit that we just did is equal to, I'll rewrite it from the start just to get a nice complete thought. So this place where we started, we combined the terms and we saw it was an indeterminate form. And so we can take the derivative of the top and the bottom. All right, so that's what happens when we combine. And now we're going to take the derivative of the top and the bottom. That's L'Hopital's rule. So the derivative of cosine is negative sine. Minus minus becomes plus. So negative sine is positive sine. And on the bottom, derivative of sine is cosine. Okay? All right, and then now we're able to plug in that 0, sine 0 over cosine 0. And we're going to be getting 0 over 1. And 0 over 1, we can simplify that. 0 over 1 is 0. So the solution, it happens to be 0, but we had to use L'Hopital's rule to conclude that. But it does happen to be 0. All right, so other types of indeterminate forms we're going to see in this section. We're going to be looking at something called indeterminate powers. And we're going to have cases that look like this. 0 to the 0 is indeterminate because we know when the base is 0, right, the exponent simplifies to 0. But we also know if 0 is in the exponent, it's going to be 1. So 0 over 0 is indeterminate. It could be, you know, what's it going to be? Likewise, infinity to the 0, we don't know how that's going to grow. Remember, one of these functions, the base might be growing faster than the exponent is growing smaller. So it's, again, it's an indeterminate form. And then finally, 1 to the infinity, again, is indeterminate, because normally when it's just 1 raised to any power is 1. But what if we're approaching 1? So it's like 1.0001. Then if we raise that to the infinite power, we are going to get bigger, because infinity is huge. So all of these cases are indeterminate. We don't know what's going to happen. So this is what an example could look like. Indeterminate powers are going to have a variable in a base or the exponent. So we can write it like this. And we saw that when we're trying to take derivatives, in this case, when there's a variable in the base and the exponent, we have to bring in the natural log. And that's our strategy here. So here's what we're going to do. We're going to take this function and we're going to call it y. So now we're going to think of this limit as the limit as x approaches a of y. Okay? So that means y is going to be equal to f of x times g of x. And again, our strategy for when there's a variable both in the base and the exponent is we take the natural log of both sides. So it looks something like this. Okay, and the reason why we do that is now that this is a natural log, we can bring the exponent down to the front. Okay, and now this is something we can work with. It's much easier to work with products of functions than functions raised to a function. Okay, so there you go. So here's our strategy. Here's what we're going to do. We're going to find how we're going to find the natural log of y. Let me start over. How we're going to find the natural log, the limit as x approaches a of y. We're going to think of it like this. So again, this is what we want. This is what we want. We want to find the limit as x approaches a of y. But y is really hard to work with, right? Because it's variable raised to the variable. That's a difficult function to work with. So what we're going to do instead is we're going to focus on the natural log of y. And the reason, we're going to bring in one of our old properties. E raised to the natural log of y is going to be what? It's y. Right? That's one of our properties. I'll write it off to the side. E raised to the natural log of y. E and the natural log kind of cancel. That's one way of looking at it. But it's going to be equal to y. So this is what this is our strategy right here. And remember, this is a composition of functions. When we're taking the limit of a composition of functions, we can take the limit of the inside function. This is something we were looking at in chapter 2. All right, so this is what we're going to be doing. Let me write it even more specific. And the natural log of y is this crazy function. All right, so just a series of substitutions. So our strategy to solve this case of the indeterminate form, we're going to want to find the limit of this thing, and we're going to look at an example right now as soon as we're done talking about this. We're going to find this limit first, then we're going to take e raised to that exponent. Okay, so we're going to find that limit first, and then we're going to do e raised to the whatever that happens to be. Okay, so there's our strategy. So let's look at an example, and we'll see how we can make sense of this. So, you know, the instructions would be evaluate or find the limit. We're going to focus on the right-hand limit of tan 2x raised to the x. All right, and remember, our first step should always be to plug in 0. And if we were to plug in 0 from the right, tangent from the right at 0 is 0. Tangent of 0 is 0. And then x at 0 is 0. So here we are. We're in the situation 0 raised to the 0 power. And again, we don't know if one of these functions, if the rate of change getting closer and closer to 0 is smaller or greater in x or tan 2x. So yes, we see it's 0 to the 0, but maybe the exponent is growing faster. Maybe the base is going faster to 0. We don't know. So we can't say that this is 1. We're not allowed to say it's 1. We're not allowed to say it's 0. It's indeterminate. Okay? And it's called indeterminate because we just don't know. Not enough information. Okay, so our strategy, and we kind of outlined it up there. We're going to call this function y. Okay, so we're going to change the problem, or just kind of reword it, let's say. We're going to find the limit as x approaches 0 from the right of y, where y is equal to tan of 2x raised to the x, okay? And again, when a variable is in both the base and the variables in both the base and the exponent, we take the natural log of both sides. And we do that because then we can bring that exponent down in front. Okay, so what we're going to do, our new strategy, is to find this limit as x approaches 0 first. And then whatever that is, we're going to do e to that power. Okay? All right, so let's write out our strategy. So we're trying to find this. First, we're going to find the limit as x approaches 0 from the right of x natural log of tan 2x. And then as I'm writing this, I realized I did an extra x, so we'll just get rid of that. Okay, so self-correcting mistakes, those are self-correcting mistakes, which is why it's always good to, you know, keep referring back to your work. And then once we find this limit, we're going to go e to that power. And I'll just write this little, you know, where we're going with this. This is what we want to find, the limit as x approaches 0 from the right of y. We're going to be tricky, and we're going to say that y is the same as e raised to the natural log of y, right? Because e and natural log cancels. That's one of our properties that we've been working with a lot. Calculus loves that, right? All right, and then natural log of y, we just said was this by our own clever manipulation. All right, and then the limit of a composite function, we can just take the limit of the inside function. And that reveals why we're using this strategy. Okay, because that's what we're trying to find. We'll do a little highlight. Oh, that was not a highlighter. So this, we're going to put as the exponent for e. And then that solves our problem. That's how we're going to solve our problem. So let's hop to it. So first step when finding a limit is to plug it in. That should always be your first step. Because if you plug in what x is going towards, and the answer is 2. That's really easy. Okay, so you should always plug it in to see what situation you're in. And in this case, if we plug in 0 from the right, let's see, x is going to be 0, and then we're going to get the natural log of tan of 2x as we approach 0. And we already said that tan of 2x is going to be 0, right? We've already established that. And it's from the right, so I'm just going to add a little right plus sign, because as you know, the natural log of x, it never reaches 0, it just reaches to the right of 0. So as x gets closer and closer to 0 from the right, our function is going down to negative infinity. Okay, so this is an indeterminate product. So we have an indeterminate product. And do you remember our strategy for an indeterminate product? We turn it into a quotient. Okay, so we're going to do that. That's going to be our strategy, and then we can use L'Hopital's rule once it's a quotient. So I'm just going to send x downstairs. So we can do that one of two ways. We can either, divide by 1 over x, or we can just give x a negative exponent. Okay, so that's equivalent. And now notice, when we plug in 0 from the right, we already know the top is negative infinity. And then if you want to draw out 1 over x, 0 from the right, as x is getting closer to 0 from the right, our function is going up. So we're going to infinity. So this is, again, an indeterminate form. So once we know it's an indeterminate form, now we can use L'Hopital's rule. We have an indeterminate quotient. Okay, so according to our rule, this is going to be equal to the limit as x approaches 0 from the right, and now we can take the derivative of the top and the bottom. All right, so the numerator, it's a chain rule. So derivative of the outside function times the derivative of the inside function. And the derivative of the inside function, again, is the chain rule. So tan of 2x, if we take the derivative of the outside function, derivative of tan is secant squared of its inside function 2x times the derivative of 2x, which is 2. All right, and then we're going to divide it by the derivative of x to the negative 1, bring down that exponent, and then subtract 2, or excuse me, subtract 1. Okay, so before we evaluate it at 0, because there's a lot of things in play here, and if you kind of look, we might still get that 0 in the denominator, or we will get the 0 in the denominator. So let's clean it up a little bit. So for instance, x to the negative 2, I'm going to get rid of the negative exponent. We can bring that upstairs. 1 over tan of 2x, that's telling us to multiply by 1 over tan 2x. So I can bring that down, that tan 2x down. Alternatively, you can think of that as multiplying top and bottom by tan of 2x, if that's a little bit easier to see. Okay, and then that cancels with that, and then we have it in the bottom. Okay, so let's clean it up a little bit. So in the top, and let's bring out the minus sign. We have 1 minus sign. So we're going to get 2x squared in the top times secant squared of 2x divided by tan of 2x. Okay? All right, so just kind of strategies, if we were to plug in the 0 right now, we would still get 0 over 0, okay? But let's look at this. So we could definitely use L'Hopital's rule and take the derivative of the top and the bottom. But look at the top. That's going to get really messy really fast. So rather than just taking the derivative right off the bat, let's clean it up a little bit. All right, and I know that trig functions can almost always simplify to something. Okay, so I'm going to break down the secant and the tangent in terms of sine and cosine. That's my hint to trig. When you're trying to simplify or prove an identity, just always go back to cosine and sine. So this is going to be cosine squared of 2x. And on the bottom, we have sine 2x, cosine of 2x. And they have the same argument, cosine of 2x, so that's a good thing. All right, so I'm going to clear the denominator by multiplying top and bottom by cosine squared of 2x. Let's see where that gets us. That cancels in the top, clears the denominator in the bottom. We're left with just one copy of cosine. All right, what do we have? So in the top, we just have 2x squared. In the bottom, let's see, we have sine of 2x, and we have cosine of 2x. Okay, so we simplified it a little bit. That's good. But we didn't simplify it well enough, because if we plug in the 0, we're still going to get 0 over 0. Okay, so we'd still have to use L'Hopital's rule and take the derivative of the top and bottom. We could the bottom isn't so bad to take the derivative of anymore, right? If we want to take the derivative of the denominator, it's a product rule and a chain rule, right? But I'm going to make it even more simple, because when we multiply the sine and cosine by each other, that reminds me of an identity, right? And then that's the double angle identity of sine, right? It's 2 sine theta cosine theta, okay? Ours looks a little bit different, but we can manipulate it a little bit, right? Here we don't have that 2, so I can just divide both sides by 2. Okay, and then in our case, theta is 2x. So instead of theta, wherever I see a theta, I'm going to substitute 2x for theta. Okay, so I have 1/2 sine of 2 theta, but now theta is 2x. Sine theta, but theta is 2x. Cosine theta, but theta is 2x. Okay, so I can substitute our denominator, which is that, with 1/2 sine of 2 times 2 is 4x. All right, and now we just have one function in the denominator. So look at this. So we have negative 2x squared. In the bottom, we have 1/2 sine of 4x. Okay? And I'm going to multiply top and bottom by 2 to clear that 1/2. So here's where we're at. And notice when we plug in x equals 0, we still get 0 over 0. Right? 4x squared, when we plug in 0, that's 0. Sine of 0 is 0. So we're still going to use L'Hopital's rule. But all of this simplifying has made our life easier, because remember, we started, where did we start? We started here, right? And taking that derivative would be ugly. It would be hard to take that derivative and then manipulate it with the limit. So we did a lot of simplifying. And now taking this derivative when we use L'Hopital's rule, it's going to be much more straightforward. we're going to use the power rule upstairs and then a quick little chain rule downstairs. So derivative of sine is cosine, derivative of 4x is 4. Okay, not bad. And then, you know, the 4's cancel. And now we're going places. What happens now when we plug in 0? I'll write it in a different color because this is a momentous occasion. We can finally evaluate our limit. 0 in the top. Cosine of 0 is 1. So we're finally looking at 0. All right. So that was intense. And let's remind ourselves where we're coming from. So we started our strategy, was to find the limit of the natural log of y, which was the limit we just found. What was it again? Natural log of tan 2x. And we did all that hard work and we said that was 0. So now, here's what we're going to do. This is going to be the exponent of our e. So do you remember that thought process? We're going to have the limit as x approaches 0 from the right. This is what we're trying to find, the original function. We called that y. We found the natural log of y, and the reason why we did it is because y is equal to e raised to the natural log of y. The e and the natural log cancel. And that's exactly what we just found. I'll even write in one more step. So the limit as x approaches 0 from the right of the natural log of y is exactly this limit. And we just said that this limit is equal to, I'll highlight so we know we made a substitution, is equal to 0. And what's e to the 0? 1. So that's our final answer. So in this case, our indeterminate form 0 to the 0 was equal to 1. All right, pretty epic problem. So I want you guys to definitely try an example of that because it's a little bit complicated, right? A lot of back and forth. I want you guys, I'm going to have you guys try out a infinite limit. Excuse me, a limit at infinity. And you guys are going to do x raised to the e to the negative x. Okay, so go ahead and push pause and see how you do. All right, well, first off, you should always test your limit. So you guys would plug in infinity. And e to the negative infinity is what your exponent would be. And here's our e to the x graph. So e going to negative infinity, we're going to 0. So e to the 0 is an indeterminate form. And we look, it's an indeterminate power. And we see we have a variable in the base and the exponent. So we're going to call, and you guys called this function y. And our strategy when we have a variable in the base and the exponent is to take the natural log of both sides. And the reason why we do that is because then we can bring that exponent downstairs. Okay, just like that. And so now, when we have indeterminate forms, we're going to first find that limit. And then whatever that is, we're going to make that the exponent of e. I'll just write it like that. We'll do pictures, not words this time. Okay, so here we go. First, we're going to find the limit as x approaches infinity of the natural log of y. So e to the negative x, natural log of x. Okay, and again, if we were to plug in infinity, e to the negative infinity is 0. And then the natural log of x, if you remember, natural log of x looks something like this. As x goes to infinity, the function's going to go to infinity. So we have an indeterminate power, 0 times infinity. So what's our strategy for an indeterminate power? We create a quotient. So I'll write in all these notes because all of these little signs in the problem tell us our next step. They tell us what strategy we're supposed to use. So this is an indeterminate product. Our strategy for indeterminate products is to make a quotient. All right, all about strategies in this section, right? Okay, so this kind of naturally is going to go downstairs because it has a negative exponent. So let's just go ahead and send e to the negative x downstairs. And now, when we are to plug in infinity, we're going to get infinity in the top as we discussed before. And now e to infinity also goes to infinity. So this is an indeterminate quotient. We can use L'Hopital's rule. Right, that's what all of this manipulation, all these strategies are for, is to get back to L'Hopital's rule. All right, and this tells us that we can take the derivative of the top and we can take the derivative of the bottom and we are going to get the same limit. Okay, I'm going to clean this up a little bit. I'm going to multiply top and bottom by x. So clearing that improper fraction. And now at this point, when we plug in infinity, we're going to get 1 over infinity times infinity. And remember, we can actually look at the product of infinities. That's something we're allowed to do. Infinity times infinity is still infinity. All right, and then what's 1 divided by infinity? What's 1 divided by an incredibly large number? It's 0. Okay, so we just discovered that the natural log, the limit rather, as x goes to 0 from the, sorry, I was stuck in our last problem. As x goes to infinity of the natural log of y is equal to 0, right? Remember, this whole thing is the natural log of y. So here's our thought process. Here's what we're trying to find. The limit as x goes to infinity of x raised to the power e to the negative x. We called that y, that function y. Okay, another way of saying y, a tricky way of rewriting y, is to use e raised to the natural logarithm. That's one of our properties. And we just discovered that the limit as x goes to infinity of the natural log of y is 0. Okay, and we can rewrite it like this because it's a composition of functions. All right, and our final step by substitution, that is 0. And e to the 0 is 1. Okay, so in closing, writing it in a more concise way, this whole expression, this whole limit is going to be equal to what?